In the previous lesson, we talked a little bit about how you get natural convection from heating the ground. And as you get this sort of thing, you get weather patterns. And the weather patterns, cyclones or anticyclones. A cyclone would be a low pressure region, air flowing into it. Coriolis effect spins it around. Anticyclone is sinking air, so that would be a high pressure sort of thing. And so you have air that flows around it in an opposite direction. And you can actually kind of look at weather maps and see kind of the direction of airflow. Now, that was all weather. We want to talk now about large-scale climatological effects. So climatologically, it kind of makes sense that the equator gets more heating than temperate latitudes. And so air would tend to rise at the equator. And so that's really where the troposphere is thickest, because the air is rising there, so it goes to a higher altitude. So as air rises at the equator, then what's going to happen is that air has to flow towards the equator, from the higher latitudes. When air flows towards the equator, then what happens is that the Coriolis effect pushes it a little bit to the right in the northern hemisphere. So instead of flowing directly towards, it flows kind of like this. And then the southern hemisphere, it flows like that. Okay. And so that means there's a definite sort of direction. The wind flows, predominantly. Now, this is not all the time, because you have weather patterns that locally can change the direction of the wind, but the dominant direction of the wind is towards the south and west, so southwest. Likewise, the air is sinking here at these latitudes, and so it spreads out. So it's sinking and circulating around this way, and so that means that it's flowing away from those latitudes up here. And so Coriolis effect pushes that to the right, and so north of where this dividing line is between the two, then the wind tends to blow towards the north and a little bit to the east. So now local land patterns can affect this, and so it's not guaranteed it's always in that direction. But from our where we are in North Texas, then we tend to get far more often a wind out of the south than we do out of the north. Okay. Unless there's like a local front or something like that. But this is the standardized pattern. Okay. So what happens though is that the air is flowing that way. It's also flowing here and merging and kind of going up. Kind of coming out and going here. So flowing one way, flowing that way, circulating, and so we have these different circulation cells in here that cause the air to again have these patterns here, and there's definite directions the air wants to flow. Okay. And so these give rise to what we call the westerlies or easterlies or whatever, because, that means that it blows you kind of towards the west or kind of towards the east. Okay. So these are what we call these convection cells. They're called Hadley convection cells. Now, at the upper level, this is what's happening, and so it actually tends to drive the storms. So at the lower level, for example, you have hurricanes, and the hurricanes here, the lower level winds are going this way, but the upper level winds tend to push the hurricanes like that. Okay, when you get up to these levels up here, the winds tend to go that way, but the upper level winds tend to push the hurricanes. So what often happen is hurricanes will be moving this way, and then they'll curve upwards when they get get up to where the weather patterns start to change, and then they'll even like curve over that way. And so you see these sort of patterns all the time with hurricane motion. Okay, again, the hurricanes would tend to down here flow this way, and when they get to where they could have been, they go up and then they kind of go off like that. Okay, now the other thing that happens though here is these are sometimes called the trade winds, because in the age of sail, when they use sails for shipping, then if you wanted to go from Europe to North America, you have to go against the wind. And so what they'd do is they'd sail down this way towards the coast of Africa and then go over and then sail up and then come back like that. So you have this big circuit right here. Okay. Now in between right here where you basically have the air coming down, a high pressure area in there, then what happens is, remember, high pressure, it tends to be calm a lot. So those areas right there, they sometimes call the horse latitudes, because if you had a sailing ship that was carrying livestock, then if you're becalmed and the wind's not blowing you anywhere, you're sitting here running out of food and water, and eventually you eat your horses. The doldrums down near the equator, or again, be kind of doldrum-like up here, what happens is the air's all coming together and it's swirling, so sometimes you get a north wind, sometimes you get a south wind, sometimes east, west. I mean, it's, and then you get storms all the time. You get very, very high altitude storms. So these storms will build huge, because remember, the troposphere is much thicker in this area, much deeper, and so you'll build these really enormous storms. That's actually something that air travel has a problem with, because these storms can get so high that if you have an airliner traveling across the equator, you're having to go through an area that at an altitude that normally has no turbulence. You're ending up with turbulence and storms and clouds, and so that's something the airliners have to be aware of. The airlines had to be aware of. So this gives rise to climatological patterns. Why does it do this? Because Earth is rotating. Because it's rotating, we have a Coriolis effect. The faster Earth rotates, the bigger the Coriolis effect. So if Earth rotated faster than it currently does, then what would happen is these storms, or rather these weather patterns, would be more extreme. So you would have winds like this in here and winds like that up here. So again, you know, it would be winds like this and like that. Okay, and the shear between the two, where the winds are in opposite directions, would make massive storms along in there. Okay, and the Coriolis effect would be much more intense, so storms would be more intense. If Earth rotated faster, hurricanes and tornadoes would be vastly stronger than they currently are, and the wind patterns would be much bigger and much more extreme. If Earth rotated slower than it currently does, then what would happen is that these patterns would be less extreme, and you would probably end up with far less weather, in fact, and you would end up with enormous amounts of rain around the equator and probably deserts all the way around here where you have the subtropical high. And so that would actually change things a bit. And of course, if you actually look right along where that subtropical high is, you actually do have a number of deserts here in different parts of the world. That subtropical high runs across North Africa, where the Sahara is, and across the desert southwest. And so, so there is something to this possibly.